Good morning to all friends. Today we have started with the another topic, that is the Norton theorem. Now, in case of Norton theorem, it is also uh, used to analyze AC as well as DC circuit, which is consist of complicated components. And for the simplification, we have to use either Thevenin theorem, Norton theorem, or superposition theorem. Means different types of theorems are available. In last time, we have seen the Thevenin theorem with its example. We have to only use the DC analysis, means it is used applicable for the DC voltage source with the resistive component. Now, if AC components, AC signal it is applied and inductor and capacitor is added in that circuit, then what happens that we cannot see in that case, but we have to see later on. Now, today we have started with the another theorem, that is known as Norton's theorem. Now, in case of this Norton theorem, the statement for this Norton theorem, it is that any two-terminal linear network containing energy sources and uh, resistance or many components can be replaced by a constant current source in parallel with the resistance. Means here it is the one constant current source must be there and in parallel with the resistance. Now here it is a complicated network or any two-terminal linear network. Now in this case, how we have to say that it is the equivalent, means Norton, by using that Norton theorem, the equivalent circuit is obtained, because if you are getting the value of load current which is flowing through this circuit, and the similar value of load current is obtained with the help of equivalent circuit, in that case the circuit which is constructed by using these components, that is by using this current source and resistance, can be same, or we can say that it is the replacement for that given component. Now here I have to draw or make the simple connection, that is here it is the constant current source in parallel with the resistance value. Means here it is that resistance value. Now okay, you have to draw proper resistance symbol. Now here it is represented as the RS, and in whatever the values, here it is the load terminals. The load terminals are X and Y, or it may be either A, B or PQ, whatever it is. Here it is, as in this case it is XY value. Here also we have to write the XY value. Now the value of load current which is flowing through the circuit, it is also same. Now we have to start with the solution example, whether it is the convert or give the proper value of load current or not. That we have to see with the example. Now here the similar example which is we have to solve previously by using Thevenin theorem, by using Kirchhoff's voltage law. Here we have to solve this example, obtain Norton equivalent circuit and calculate the current flowing through load 10 ohm load resistor. Here it is that 10 ohm load resistor, and we have to obtain the current flowing through this device. Now firstly, the steps for this case, that we have to, most important, means once you have to understand the steps for this case, you can easily get the output, or you can easily solve the example. It is not necessary to get that is how to remember it. Only 2 or 3 steps are sufficient, as like Thevenin theorem. Step 1, what is the requirement to calculate Norton current or Norton equivalent current? Norton current in bracket IN. Norton current. What we have to do? Disconnect load resistor. Disconnect load resistor, and the load terminals are shorted, or make it short. Means what we have to do? We have to disconnect this load register, and these terminals are make short circuit. Now the circuit must be represented like this. Now here the voltage source must be required because we have to find out the current flowing through the circuit. Here it is that R1 resistor, R2 resistor, then R3 resistor, and these terminals are short circuited. Means here you have to make the short circuit terminal. Now in this case, the terminals are represented as A and B. The value for the resistance are again same, that is 20 ohm. Here it is 20 ohm, 10 ohm, and here it is the short circuit. Now, how to calculate the current flowing through the circuit? Now, it is calculated by using the knowing the total current which is flowing through this circuit. That is, here it is 10 volt. Now, the current flowing through the circuit, that is I is equal to I, which is flowing because of this supply voltage. Now, here I, it is nothing but phi divided by R. Whatever the phi component and whatever the R component, that we have to see. Phi, it is nothing but supply voltage, and R, it is nothing but total resistance of the circuit, because these are the two paths for the current flow, and it is the 10 volt. Now resistance value, this is that R1 resistor. Means here we have to make one mistake, that is whenever we have to calculate the current, we must calculate the equivalent resistance value from this terminal. But whenever we have to calculate the equivalent resistance value, that is RTH or RN in this case, we have to obtain the from this output side. Means from this side we have to find out that resistance value. Now here, that is R1 must be in series with the parallel combination of this R2 and R3. Here it is that R1 value. R1 must be in series with R2 parallel R3. Now for this case, what we have to get? We have to obtain the equivalent resistance, that is 10 divided by, it is 20 plus, now 20 into 10 divided by 20 plus 10. Now this value should be approximately becomes as 10 divided by 20 plus, it is 200 divided by 30, and if you are cancelling the 0, that is 20 divided by 3, and its value should be approximately becomes as 6.667, and it is 10 divided by 26.67667. Now these current values, its value should be approximately 0.3775 ampere. Means here you can get total current. Not it is not the current equivalent current, but it is total current flowing through the circuit. That is I is equal to 0.375. Now we have to find out current flowing through this R3 branch and current flowing through this AB terminal. That we have to find out. And for that purpose, what we have to do? We have to use the parallel branch theorem. Parallel branch theorem, what is that? The current flowing through this voltage across this terminal and voltage across this terminal, it should be same, because the value of current, it is only distributed. That is, some amount of current it is allotted to pass through this R2, some amount of current it is allotted to pass through this R3, and therefore by using parallel branch theorem. Now what is that parallel branch theorem? We have to find out the current which is called as IN. Here I have to write the IN. That is value of I, we must know. Then it is divided by current must be flowing, this current must be flowing through this R2 as well as R3. Therefore it is represented as the R2 plus R3. Now here one resistor must be required, and that resistor, it is nothing but the current which is flowing through that branch. We cannot consider that resistor, but the component which is not used in that circuit. Means here the current flowing through this R3, that is our required current, but we have to find out, or we have to write, the value of resistance that is equal to R2 here. Now here, by putting the values, we have to get the value of equivalent Norton current. What is that? Here it is 0.375 into value of R2, it is 20 ohm, divided by 20 plus 10, that is nothing but 30 ohm. It is, its value should be, if you want to calculate the value of equivalent Norton current, it is not the current which is going to be load terminals, because we have to find out it. What is the value of load current? Means the equivalent circuit which is present, that is having this value of equivalent current, it is nothing but that Norton current, and its value should be 0.25 ampere. Means here current should be obtained. Now step second, for the step second, I have tried in on next page, that is step second. For the step second, what we have to do? We have to obtain equivalent resistance, that is to calculate Norton equivalent resistance. Now what is that Norton equivalent resistance? It is similar to that of the resistance which is obtained in case of Thevenin theorem. Means Thevenin equivalent resistance, it is exactly same to that of Norton equivalent resistance. Means whether it is Rn or whether it is Rth, in both cases the value should be same. Only change it is that the current which is to be obtained by Norton equivalent current, it is called as short circuit current. And in case of Thevenin equivalent voltage, we have to represent it, that value in terms of open circuit voltage. Means these are the terms that you must have to remember. Now the equivalent, to calculate Norton equivalent resistance, we have to replace or disconnect the short. Disconnect the short across load terminals. Disconnect short across load terminals. Then replace voltage source by short circuit, and current source by open circuit. Remaining their internal resistance, if any, means if there is resistance should be there, then that resistance value we have to remain as it is. Remaining their internal resistance, means in some case the internal resistance value should be also present, but we cannot consider for this case internal resistance. Remaining their internal resistance. Now the circuit should be looking like this. Now the voltage source, it is shorted, and the value of R1, value of R2, and here R3. Now here it should be make open terminals. Here A terminal, B terminal. The resistance value should be 10 ohm. Here it is 20 ohm, 20 ohm. Now in this case, what we have to do? We have to obtain the Norton equivalent resistance, which is obtained from this terminal. Means from this outward side. Again, in last time I have given that whenever we have to calculate the equivalent resistance from this side or from this side, what we have to do? We have to put this terminal to be hanging condition. Means once it is put in that hanging condition, we have to start the condition. We have to start the condition for Now the condition it is that the terminals it is made of, with hanging condition, and automatically the resistance values are in the specific way, and how it looks, that is the most important. Means once you have to make the simplification of any circuit, that is starting from a point, I have to put one hanging condition of a, that is here it is the one resistance value, that is R3. Then there are two paths. Here there are two paths should be there. One it is the 20 ohm resistance, another it is also 20 ohm resistance. And these two terminals are again connected. These two terminals are again connected, and finally you can get the point P. Now you have to simplify the network, that is whether which are the parallel combination and which are the series combination. Now here it is the R3 register, R1 register, R2 register. Now the simplification of circuit should be very easy. What it represents, R1 it is parallel with R2, and parallel combination must be in series with this R3, and it gives the equivalent resistance, that is Rn. Now here we have to find out Rn value. Rn it is equal to R3, means I have to start in from this point. R3 must be in series with the parallel combination of R2, R1, R2. Now the equivalent resistance, that is Rn, equal to, what is R3 value? It is 10 ohm plus 20 into 20, that is R1, R2, 20 ohm, and 20 plus 20 ohm. Now one more thing that I want to give, that is whenever you have to find out the parallel equivalent resistance of this parallel combination, if the values are same, then the resistance value should be exactly half of the given values, half of the given values. And if they are different, in that case, whatever the smallest resistance from these two, again we can get the smaller value from that both values. Means whatever the smallest, again from that smallest, again we can get the smaller value of equivalent resistance. Means that thing you must have to remember, that is 10 plus, it is value, if you are making simplification, its value should be also 10, and you can get the simplified value, that is 20 ohm, that is Rn you have to get to be 20 ohm equivalent resistance. Now by using step 3, what is step 3? Step 3 it is nothing but we have to obtain equivalent circuit by using IN, that is current source, and RN, equivalent circuit becomes equivalent circuit becomes that is here the current source value, its value should be approximately sorry, it is 0.25 ampere IN, in parallel with the resistance value, its value should be Rn equal to 20 ohm, and the load terminals, that is A, B, in which the resistance should be there, its value should be RL equal to 10 ohm. Now we have to find out the value of load current, and that load current it is obtained with the again parallel branch theorem, and that parallel branch theorem that we have to again represent, that is value of IN, current flowing through this IN, that is RL, that we have to record, which is called as load current. IL equal to, what is that IL equal to? We must know the current at this terminal, it is IN into, now resistance which current, if current flowing through this component it is required, we have to take the another resistance. If we require the current flowing through this component, we have to take this resistance. Now we have to find represent, that is it is Rn, Rn upon Rn plus Rl. It is. Now, if you are putting these values, that is value of In it is 25 ampere into Rn it is 20 ohm divided by Rn it is 20 plus 10, that is 30 ohm. Now, if you are making the simplification for this case, it is 0.5 divided by 30, and if it gives, that is, sorry, 25 into sorry, 0.5, 25 into 2, that becomes 5 upon 30, and its value should be again represented as 0.1667 ampere. And if you are represent with the help of the Kirchhoff voltage law and Thunian theorem, in that case also we have to obtain the same value, is by using the Kirchhoff's current voltage law, by using Thunian theorem, by using Norton theorem, we can get the same result, and therefore we have to say that our circuit analysis should be exactly uh, having exact value. Means here the value of load current it is represented like this. Now, if you are compare this result with another, then in that case the value should be same. Now here we have to stop, and in another lecture we have to see next term. Thank you. Thank you all.